Okay, I think we'll start. So last time we talked about parametric surfaces and areas of parametric surfaces. So what was the idea? We have a region D in the UV plane and a mat R that you can think of as lifting D off and twisting it to fit on S. Okay, so that's a parameterization. Now, how did we tackle the problem of finding the area of such a surface? Because all these sort of curves and bends make this quite hard to compute. So what you do, we did what we normally do in calculus. Yes, we broke it up into small pieces and we tried to approximate the area. Yes, of each piece, and then we sum, and then we take finer and finer subdivisions. Yes? Okay. So we found that the area of such a piece was roughly RU cross RV, delta U delta V, where again R is the parameterization. Okay, so what's our goal for today? Goal number one, integrate functions over surfaces. Okay, so we'll talk about examples of this. Develop a notion of orientation, and then develop a notion of flux. Okay, so some examples. Let's say I have a surface S with mass density function delta, or charge density, and then it would be charge on S. Yes. Then the mass of S, you would like to compute how heavy is this like metal sheet that's sitting in space. Yeah, that's a question that as an engineer you might want to answer. Okay. Right, so that's an example of integrating a function on the surface. So, example of flux. You can think of a problem where you have a membrane or some sort of vessel that allows water to pass through, or some sort of fluid. Yes? And you might want to say, well, what is the rate at which water is passing through this surface? Yes? Okay? If I have this metal sheet and I heat it up, I might want to know, well, what's the rate at which it's emitting heat? Yes? Okay. What other things do we think of when we hear the word flux?
Magnets.
Say it again.
Magnetic flux.
Magnetic flux, very good. Okay, so you're thinking of like a magnetic field coming through a surface. Yes? Anything else? Yep.
Electric flux.
Electric field, yep. Okay, very good. Right. Now, at the core of each of these examples, like water passing through a membrane, heat energy coming through a surface, magnetic and electric charge coming through a surface, yes? You have this core idea of something flowing through a surface. Yes, the rate at which something flows through a surface. Okay? Which makes sense because flux comes from the Latin word fluxus, which means flow. Okay? Right, so let's get into surface integrals. So we can think of the relationship between calculating surface area and calculating surface integrals similar to how we thought of calculating arc length versus calculating line integrals of functions. Okay, so that's a thing to keep in mind as we go through this sort of construct. Right, so before we get into the details here, let's go back. Right, how can we alter this to instead of computing the area of this sheet, let's say it has a mass density and I'd like to compute the mass. Right? How can I use the sort of core philosophy in this idea to compute the mass of the sheet? What's my first step going to be? Yeah.
Break it into smaller.
We're going to break it into smaller pieces, right? We're going to divide it up into a grid like this, and then what are you going to do? You're going to calculate what? If we want the mass of the whole thing, what are we going to do? We're going to calculate the mass of.
Sum the densities.
Say it again.
Sum the densities.
Yeah, sum the masses of each piece. Yeah, you're going to calculate the mass of each piece. You're going to add them all up, and you're going to take a limit. Does that make sense? Okay, good. Right. So here we have D fitting onto S. We divide into grid lines, and we arrive at this picture. Right. So what we said there, what Dylan said there, was we're going to try and get the idea of what is the mass of this small piece. Yes? Okay? Now, your density function generally in real life is quite well behaved. Yes? You don't expect to have like very, very thin, not so dense, and then right beside it extremely dense. Does that make sense? You expect if you zoom in far enough that it like varies continuously. Does that make sense? Right? So, the density on this small patch is approximately constant. It doesn't change too much. in this small patch. Does that make sense? Right. So, how would you compute the mass of something? How would you approximate the mass of this patch? If I told you, yeah.
Do the area of the patch and then just multiply it by the roughly constant density.
Very good. Right. Very good, Joe. You take the area of this patch, which conveniently we have already done. Yes? And then we're going to multiply it by the density. And then we're going to sum up. Yes? And then what are we going to do? Take finer and finer sub-intervals, and then we're going to get this integral, right? So, the mass of this patch should just be the density on a point on the patch, the density at a point on the patch times this. Does that make sense? Okay. So, we arrive at here. Here's the density at a point on the patch times the area of the patch. Yes? Okay? And we're going to sum that over all the patches and take a limit, and we end up with this. Okay? Any questions? Okay. Okay. So, in general, for a general function f, like we need not have a mass density, we can do this for a charge density, etc. Yes? So instead of, if we want to integrate a function f, we just have integral over d, f, r, u, v, r, u cross r, v, dA. Magnitude r, u cross r, v. Okay. Now are there any questions? Are we still good? Okay. So, let's look at an example. Let's say I want to compute the mass of a sheet of metal that looks like a parallelogram, and it's, well, it is a parallelogram, and it's parametrized by this R. Okay? How would I go about doing that? Well, geometrically what's happening first? We have this, so this region, u going from 0 to 1, v going from 0 to 2, looks like this. Yes? And what R is doing is it's twisting it into the x, y, z and fitting it onto S. Yes? So the formula, again, was integral f r u v ru cross rv du dv, where f here is this density function. Okay? So, the first, I have three things to do. I have to figure out what this looks like. I have to figure out what this looks like. And I have to write bounds for d. Okay? So, let's go with finding what delta of RUV looks like. So delta of RUV, well, RUV is u plus 1, comma, minus u plus v, comma, u. So, if delta of x, y, z is z squared, then delta of this is just going to be u squared. Very good, right? So, let's calculate RU. RU is going to be what? We take the partial derivative with respect to u of each component. 1 minus 1, 1. Okay. Then RV is going to be 0, 1, 0. And I want to take the cross product. So, first of all, I'll just take the cross product. If we take the cross product of these two vectors, we are going to get minus 1, 0, 1. I skipped the calculation there, but we're used to cross products at this stage. Okay. Now, to find the length of this, I square each of the component and take the square root. So I end up with the square root of minus 1 squared plus 1 squared is just the square root of 2. Okay? So, if I call this I, then I equals, well, d is u goes from 0 to 1, v goes from 0 to 2, of u squared times root 2 du dv. Yes? Okay? There's no v dependence, so it's just going to multiply the answer by 2. 0 to 1, u squared du equals 2 over 2, u cubed over 3 between 0 and 1 is 2 over 3. Okay. Any questions about this? Yeah.
Just how did you get delta u like equals u squared?
So delta xyz, if you feed this thing a point in three-dimensional space, it looks at this and ignores it, looks at this and ignores it, and then it squares this. Does that make sense? So if you feed it a u and a v, you feed r u and a v, yes, and then r feeds delta, yes, which is what this means. Okay? So when you feed u and v to r, you get this, yes, and then delta sees this and it ignores this, and squares this. Does that make sense?
Yep.
Okay. Right. Any other questions? Okay. So, remark, we can develop an idea for the center of mass on a surface analogously to how we did it for a region in the plane, okay? So, I'm not going to talk about this because I think you're going to see problems in the tutorial about this. Okay? So, the special case of where S is the graph of a function. So, all I told you was that S was a parameterized surface, yes? We saw in the previous lecture how to parameterize a sphere, yes, etc. So you need not have a graph of a function. But in the special case where S is a graph of a function, and remember we talked about what the graph of a function looks like if it's z equals g of xy, you're taking in points on the floor and you're developing this canopy up here. That makes sense? Yeah, remember that? Right. So, if you were to go through the calculation for, we go back here, if you were to go through this formula, okay, with the knowledge that, well, for a graph of a function, the parameterization is this, r of xy is x, y, g of xy. And why is that? Because when I'm making this surface, what am I doing? I'm going to a point on the floor, x, y, yes? I'm keeping x and y the same, and then I'm putting in z as g of xy. Yes? Okay? So parameterization for a surface is just this. Right? So instead of using these, I just have x's and y's, but we don't care because they're just letters. Yeah? Okay. Right. So if you were to flesh out this formula with this parameterization, you arrive here. Okay? Which is a very useful shortcut. Okay? So, example, which you guys are going to do in groups. Okay? So, let S be a surface given by Z is y minus x squared above the region D equals this set of x's and y's. Okay? Let F be equal to this. Compute the integral of f over this surface. Okay? So, I'm going to give you a couple of minutes just to figure out how to set up this integral. Okay? You don't need to finish it out. Just make sure you understand how to set this up. Okay? So, in pairs, talking, yeah?
I think you start by plugging y minus x squared yeah, just let's write it down here. X squared. Oh, that's some fun. Oh yeah. So that would be dgdx is negative 2x, and then dgdy is 4x. So we just have to plug those values in. 4x plus 1. It's really not bad. Okay, I got yeah, I just got F1 Yep.
Yeah.
So that's you got 4 squared plus 2.
Yes. So what are you doing? How do you integrate that?
You get to use yourself because you have the 4x squared and then you get the x's outside. Because x goes what you got on the inside of that?
Okay, so we don't even figure out how to set it up. Okay, that might want to come up and show it on the board. Or if you're camera shy, you can just shout at me. Okay? Would anyone like to shout at me? Ben.
Can I just tell you?
Yeah.
Okay.
So we have a couple of things to compute, yeah? We have to figure out what this looks like. We lost the job. We have to figure out what this looks like and what this looks like. Yes? Okay, so.
Okay, so it gives us that the g of x of y is equal to y minus x squared because that's the surface.
Uh-huh.
So then for the f of x, y, z, where it says z, you plug in the y minus x squared. So it's x squared plus x minus y plus y minus x squared.
Okay.
So that's just x.
Okay. Now what?
And then so you do the part inside the square root, or that's what, yeah.
Yep.
So that equals to -2, or -2x squared.
Uh-huh.
And then 1. Or for, yeah, g of y is 1.
Okay, so.
And then so then the inside is 2 plus 4x squared, or 4x squared plus 2.
Very good. So this integral becomes, what's the last thing you have to do?
The balance is just from
Balance, very good.
so y goes from 0 to 3, and then x goes from 0 to 1.
And then we have x squared very good. Thank you, Ben. Yeah? Right. So, how would you do this? How would you tackle it now? Yeah, in
Use of.
use of, okay? So, you see that this differentiates to a constant times this, you're going to do it by use of, okay? So, just to finish the problem out, there's no y dependency, yes? Okay, so that'll take care of itself and just multiply the whole thing by 3. So, you're going to let u equal 4x squared plus 2 and carry on. Okay, any questions on that? Okay, very good. Right. So, remark. In the same way that we can construct graphs of functions taking in x's and y's and creating a canopy up here, yes? I could take in y's and z's and create a canopy out here. Does that make sense? I could tell you if you take in a y and a z, it spits out an x value, or actually I've done it the opposite. If you take in an x and a z, it spits out a y. Okay? Or I can take in a y and a z and spit out an x. Okay? There's nothing really geometric going on here except you look at what would have been your graph and then you turn your head. Does that make sense? Okay? So it's all you've done is swapped letters. Okay? You've swapped what you consider to be x and y and z. Okay, and you end up with these formulas. you end up with these type of formulas, which are completely analogous to this. Okay? Except you swap the roles that each variable is playing. Does that make sense? Any questions? Okay. So, yeah. Oh, sorry, Jordan.
Say the swapping thing again with turning the head.
Yeah, so, like if I had a graph where it takes in an x and a y and splits out a z, it would look like some sort of canopy like this. Yeah? Or it could look like a bowl like this. Okay? Instead, I could give a machine that takes in an x and a z and splits out a y. Yeah? Okay? So geometrically all it corresponds to is like I've looked at my bowl like this and someone's giving me a bowl that looks like this and I just do this. Yeah?
Okay.
Right. So, any other questions? So, let's say you have a piece, so S is a piecewise smooth surface if pretty much it's some sort of Franken surface, right? You've taken the blue surface and you've welded it onto the, you've taken the blue cone, you've welded it onto the green cylinder, and then on top you've welded on this orange dome. Yes? Okay? So, if you want to integrate a function over this entire sort of thing, yes? It looks like a spinning toy thing. Yeah? Okay? You integrate it over each piece separately and add it up. Does that make sense?
Yes.
Yeah, good. So that's all this boxed formula means. So if you want to integrate over this whole thing, just integrate over each piece and add them up. Okay, so moving on to orientation. So let's say I have a metal object S, which is emitting heat energy. Okay? If we computed this flux, should it be positive or negative intuitively? What do you think? If it's emitting heat energy. Some people say negative. Who thinks positive? Who thinks negative? Okay, right. Sort of half and half-ish. Right, so, new hypothetical. Now say I have a metal object S which is losing heat energy. If you computed this flux, should it be positive or negative?
Negative.
Okay, so everyone's kind of switched. Even the people who said positive, the switch. But these scenarios are exactly the same. Yeah? All I've changed is this perspective. Am I thinking of the environment receiving heat, or am I thinking of this thing as losing heat? Yeah? Right? So, that's the kind of concept of orientation. Now, I have to choose. There's no real should this be positive or should this be negative. All I did is I changed the word emit to lose. Yeah? So it's a matter of perspective. Yes? You want to see like what direction am I going to call flowing positively, or what direction am I going to call flowing negatively? Okay? Any questions? Okay. So, conclusion. There is no overall should. You have to make a choice. You have to make a choice of orientation. Okay? So, orientation is technically a choice of continuously varying normal vector n. Now, what does that mean? N points in the direction you're going to call positive. Does that make sense? Okay? So, now, if I have this sheet and I have heat flowing up through it, yes, that's going to be what type? Positive or negative?
Positive.
Positive. If it's flowing this way,
Negative.
negative. I could just as easily take all these arrows and decide that downwards is positive. Does that make sense? Okay? So orientation is a choice. Okay, and what does continuously varying mean? Continuously varying means that if you follow along, the arrows behave nicely. Yes, you don't get jerks where it flips under. Does that make sense? Okay? So, you say that a surface S equipped with an orientation N is an oriented surface. Okay? So this is an oriented surface. Okay. Any questions? Yeah.
If there was some sort of behavior where like your N was getting like closer to 0 and then it like flips. Like you say you don't want it to flip on you, but if there's like normal behavior, is it okay if it does?
So let's imagine a sphere, right? And if I want to be at the North Pole Yes, and let's say I can decide whether to point up or point down. Yeah? So let's say I point up. Right? What's going to happen as I move along now?
It'll slowly rotate.
Yeah, there you go. So there's kind of an example of what you're talking about, I think. Yeah? Yeah, very good. So it doesn't always have to point up. It doesn't always have to point down. Depending on the surface, it can point in a number of different directions. Okay? There are even some surfaces where you cannot put an orientation on it. Okay? Which is very weird. But have you heard of a Mobius band?
Yeah.
Okay? If you haven't heard of a Mobius band, take a strip of paper, right? Put a twist, and then staple it. Right? And then try and see if you can put an orientation on it. Okay, we will talk about that in tutorial if you want. Okay. Some food for thought. Right, so a surface S equipped with an orientation is an oriented surface. So really we can only do flux integrals on oriented surfaces, because what does flux mean if I don't already have a pre-described notion of where is positive and where is negative? Yes? How am I meant to compute this quantity if I don't know what sign it should be? Does that make sense? Okay. Right, so special case, if S is the graph of a function, okay, so it looks like this canopy, you can talk about upward or downward orientation. Okay? So the picture hopefully explains what I mean. All pointing up, all pointing down. Well, down-ish, it can turn a little bit like this, but they're all under the surface. Does that make sense? Okay? So if someone hands you a graph, they write down z equals something, the way to compute the upward pointing unit normal is this formula. Okay? Which comes from the idea. Remember when we did grid curves, we talked about the RU and RV? Okay? You can do an analogous thing with Rx and Ry. And this formula looks mental, but really all it is you've got this vector and you've just made it unit length. Does that make sense? And you would want the orientation to be unit length. Yes, because all you care about is a direction. What direction is positive, what direction is negative. Yeah? So you don't want it to have a length other than 1. Okay? So, exercise. Find the upward pointing unit normal to the surface given by z equals x squared plus y squared. So that's something you can do later. Okay. So, if S is a parametric surface, so we talked about if S is a graph, if S is a parametric surface represented by RUV, here's the formula for computing a unit normal vector across it. Okay? RU cross RV divided by, again, the length. Okay? So, if I have this orientation n, yes, how can I get the flip? How can I get the opposite one?
Negative.
Take the negative of it, yeah? And what that does is that you have your n going along your surface and then it just goes boom. Yeah? Yeah.
So the choice of direction is pretty arbitrary.
Exactly. It's your own, it depends on your perspective for each problem, okay? Yeah, exactly. Okay? Although with certain theorems it'll be important. Right? Remember those assumptions in Green's theorem where you have your curve going counterclockwise and you're like, why? Yeah, we'll come into it. Yeah. Right. So, there's another exercise you can do. Just find the unit normal of this. So this is pretty much just to get used to the two formulas. Yeah. So, let's say we have a closed surface. You can define outward and inward pointing unit normal. So I have the sphere and I have something flowing through it. I can think about it's positive if it flows outward, yes, or positive if it flows inward. Yeah? Does that make sense? Right. So, let's say I have water moving on the surface of the sphere. Right? So I have water moving like through or around the surface of the sphere. Right? Let's take the case where the water just shoots out of the sphere. Yes? And I take the outward pointing orientation. If you calculate the flux, what sort of number do you think you'll get? Positive. Okay, if we're taking the outward orientation of the water is flowing out. Okay? Now, let's think of a scenario where instead the water just flows around the surface. Okay? What do you think the flux should be?
0.
0. Nothing's passing through the surface. Does that make sense? Okay? So, the water in this scenario where it's flowing around the sphere could be moving much faster than the water that's flowing through the sphere. Yeah, it could be absolutely just, yeah, some sort of horrible sphere of water that's just rotating. Okay? Versus like calmly pushing water out into around it. Okay? So, there's an idea that when we're calculating flux, we only really care about the flow that's going in what direction? Outward, in the direction of the normal vector. Do we see, if the water is rotating, what direction is it moving?
Perpendicular.
It's like perpendicular to the normal, which is, begins with T. Tangential. Yes? Does that make sense? You want to ignore everything that's moving tangentially and only pick up everything that's moving in the normal direction. Very good. Okay. So, if you, let's say we're on a sphere. Okay, here's the sphere. Here's the origin. And let's say I come out to a point P. And P is equal to XYZ. How would I find the unit normal to the sphere at P? If I handed you a soccer ball, yes, and I pointed at a point on it, and I asked you to like make the unit normal out of like a stick or something, yeah, where would you put it pointing? In the same, yeah. So Ben meant this motion, yeah, which is in the same direction as P. Okay, you'd find out what direction P is, and then you'd have N, and it's going to be the same direction as P, and it's going to be unit length. Does that make sense? Okay. So the vector that's in the same direction as P is P. Yes? And then we want to make it unit length. Okay? So N should be, what's the length of P? X squared plus Y squared plus Z squared. And we want to take 1 over that times X. Okay? And if we're on a sphere of radius R, then the distance P is from the origin should be 1 over R. Yes? Which is this one here. Does that make sense? Okay, so that'll be useful when you're doing problems later on in web assignment and whatnot with the where you're going to need the unit normal to the sphere. Okay, any questions? So, suppose we have an oriented surface S, unit normal N. Okay? So I've got my surface, I've drawn all my normal vectors, I've decided that up is positive. Okay? And let's say I put a vector field on this surface. Okay? So I have some vector field which could be, it could be a flow for magnetic, electric, water, yeah? We have this scenario. Okay? So, recall from the examples we talked about at the start that we had this core idea that the flux should capture how much F flows things through S. Yeah? Okay? How much F is flowing, how much F is causing things to flow through S after we've written that. Okay? So, as with all sort of establishing all these formulas, what are we going to do? If we want to establish something on all of S, we're going to take patch and zoom in. Yeah? Okay, so let's zoom in on a patch of area delta S. So here's our patch of area delta S. Right? So, on this small patch, our vector field F, oh, vector fields F and N, I was right. Vector fields F and N are well behaved. So again, F shouldn't vary too much on this small patch. Okay? And neither should N. Right. So, how am I going to figure out how much is flowing through this? If we think of F at the rate of F as the velocity field of some fluid, okay, that is on this patch, and it's moving at speed v. So I have this patch sitting in space, yes? I have my fluid particles flowing through, okay, with velocity f, okay? And I want to capture the rate at which the volume is flowing, the volume of water is flowing through, yeah? Okay, so I have the patch, I have the velocity field f on this patch, okay? And I think of f, let's say, has speed v. Okay? So, if f is like v meters per second, right? If I let a second pass, okay, this should shoot, let's say, v meters of water through this corner. Yeah, just like think of it like a rod made out of water. Does that make sense? Okay. Then over here it'll get another one. Yes? And in the other corner another one, and the other corner another one. Everywhere you're going to spit out these rods. Yes? And if you look at them as a whole, what will it be? It'll be a volume. It'll be a cube of water. Yes? Does that make sense? Okay? And that's kind of the rate at which this thing is pumping out like volumes of water. Yes? Okay? So, I'd like to figure out, well, what is the volume of this box? Because the volume of this box is how much water F is pumping out per second on this patch. That makes sense? Okay? So, how do you find the volume of a tilted box? Base times perpendicular height. Yes? Does that make sense? Okay. So, we have here we have the drawing on the projector is much better. Okay. We want to figure out what is this height. Okay? So, we want to figure out how much F points in the direction perpendicular to the patch. Yes? What points perpendicular to the patch? N. So, if we want to figure out how tall this box is, what should you do? We're going to find the component of F that points where?
Direction.
And the direction is a normal vector, yeah? So we have comp of Fn, which was F dot n over the length of n. What's the length of n? 1. So this is F dot n. Okay? This is perpendicular height. So, what was the area of the base? It was just some delta S. Yeah? So what's the volume of this box? Ben pointed again. Okay. F dot n times delta S. Okay? Now, this is the volume that F pushes through a patch. How do I get the volume that F pushes through the surface? So I'm going to add them all up. Very good. Right? So, when we add them all up and take a limit, we arrive here. The integral of F dot n ds. Okay. Any questions? Okay. I'll let it sit with you and then maybe you'll have questions. So, we'll look at an example. Let's say again that S is the unit sphere, x squared plus y squared plus z squared is equal to 1. Then F be the vector field x, y, z, and let's compute the flux. So what does the vector field look like? What does the vector field xyz look like? If I'm at a point in the sphere, where does it point? That direction. Very good. Right? So, if we want to compute this, we have that, and now I've introduced a piece of notation. This ds vector, okay? In text you might see it as ds with s is bold, is just n dot ds. Okay? So back here, this ds vector is just n dot ds. Okay? Right, so if I want to compute over s. Well, they give me f, so there's nothing to compute there. Yes? They give me n, so I can pretty much write down what this is. Yes? So, we have n for an arbitrary sphere, is 1 over r xyz. So, in our case, what's f dot n going to be? Well, first of all, what's n?
X, Y, Z.
It's just xyz, so what's f dot n? X squared. Yes, so Cameron jumped a step ahead of me. F dot n is x squared plus y squared plus z squared, which if we're on the unit sphere is 1. Okay, so to compute this, I just want to integrate 1 ds. Yeah? Okay, but I can just erase this. What does this look like? This is the formula for surface area. Okay? So, very good. This is just the surface area of this surface, which is the unit sphere. And what's the surface area of the unit sphere? 4, and if r is 1, 4 pi. Okay? Okay. Any questions? Yep.
How did you get n equals x, y, z?
So, did this make sense up here?
Yeah.
Where we have n is the unit normal to any sphere?
Yeah.
Yeah? No, yeah. Okay. So, here in our case, r is 1, so it's just x, y, z. Okay? Because you want the unit normal to point in the direction that the point is at. So if p is at x, y, z, you want n to continue on x, y, z. And because we're on the unit sphere, we just plug in r as 1. Okay, yes, Ben.
What does that mean in terms of the flux?
So this is saying that if I turn on a spout of water at each point, okay, that's like flowing out at a rate of like 1 meter per second. Okay, so if I have water flowing out of every point on the sphere radially at 1 meter per second, every second it will contribute 4 pi meters cubed water into the environment around it. Okay. Good. Any other questions? Okay. So, special case, if S is given by RUV, so it's parameterized by R. Okay? So we have the same formula, N. Now remember that formula in the box. If S is parameterized by RUV, I have a normal vector RU cross RV over the length of this. Yes? Okay. Now, ds from the last lecture was roughly, or was RU cross RV dA. Yeah? Magnitude of this. Okay? So, what do you get? You get this nice cancellation. Okay? And we arrive at this form. Okay? Now, I want to emphasize how useful this is. Okay? Okay? Look, if I asked you to compute n, what do you have to do? You have to compute RU cross RV, and then you have to find the length of this thing, and you've got some horrible formula that probably involves a square root. Yes? Then you're going to multiply it by ds, which is this magnitude. Yes? But it's the same thing, it always cancels. So if you normalize n, yes, you're going to have to go through this horrible rigmarole of calculating this thing, and then you're going to realize, oh, I have to calculate it again, and then you're going to realize, oh, it cancelled, I shouldn't have done anything. That makes sense? Okay? So this formula will save you a lot of time and pain. Yeah? Okay? It's different to the first one because this is not n. Okay? Like here we have f ds is f dot n ds. Okay? So it looks like they're in the same places, but I want to emphasize this is not n, okay, because it's not necessarily unit length. And this is not ds, but you have this lovely harmonious cancelling. Okay? And this is going to be very useful. Any questions? Okay. Right. Again, so we check these cases. What does the formula look like? If f is the graph of a function, z equals g of xy, then f dot ds is this formula, where f is p comma q comma r. Why is this true? So, what did we say before? If we go back to this formula up here. Okay. RU cross RV. Okay. So, here this is going to become RX cross RY. Okay. Where R, recall, of XY is X comma Y comma G of xy. Yes? Okay. You would be able to compute this. Yes? Okay, what would Rx be? Okay, what would Ry be? Now, as an exercise, you can take the cross product of this, plug it in here, and see you arrive at this formula, which again is going to save you time. That makes sense? Okay. Any other questions? Yeah.
Wait, what's the PQR?
So f, oh, very good. I should include that. So f as a vector field, f of x, y, z is p of x, y, z, comma, q of x, y, z, comma, r of x, y, z. Okay. So in these formulas, again, when you're integrating over d, you're going to have to replace z with g of x, y. Okay. Yes.
So you're saying after you cross the r of x and r of y, then you cross it again with,
Or you dot.
no, dot product.
Exactly. Very good. You're going to arrive at this. Yeah. Okay. Any other questions? Okay. So, really quick, have this example. So, the last 2 minutes was set up this example. In pairs and whatnot. Yeah. Okay, so someone shout at me again, just so we finish on time. What is g sub x? First of all, what's g of x?
X squared plus y squared.
X squared plus y squared. So g sub x is 2x. G sub y 2y. So so we're going to fit into this formula, right?
Yeah.
What's minus p?
Y.
So it's p q r. Yeah. So minus p is
Oh, X.
yeah. Okay. So x times 2x plus what's minus q? Y times 2y. What's r?
X squared plus
X squared plus y squared. And I have dx dy integral over d. Okay? Flesh this out, what do you get? So overall, 3 times x squared plus y squared dx dy. What are you going to do? Switch to polar. Very good. Okay. Right. So office hours today, Professor Edlin has 3 to 4. On Thursday I have 3 to 4 and 6 to 7. And the problem session today is 6 to 8. Sorry, that's a typo. Okay. Thanks very much.